Okay, today for Chem 100, the syllabus in schedule has this day listed as a buffer day. When I have face-to-face class, it takes a little longer to get through the material. So I schedule these buffer days in there for classes that have lots of face-to-face students. But since this modality allows students to participate either remotely or through the web, I find myself with extra time. So today, instead of buffer, I'm going to complete the review for exam 5 on chapter 9, the chemical quantities. And then next Thursday, which would normally be scheduled for the review, I'll be here to answer questions. And I'll stay for at least half the class period. And that way, if you want to zoom in or show up in person and work out some problems, then I'll be here. But for today, we're going to do the review for chapter 9, exam 5. We're using the review document that I hand out in class, and that's available in the exam 5 module. We're going to use the my version, where I have highlighted particular questions and problems that I want to be sure and cover. All right, so let's get started. Number 1. Consider that calcium metal reacts with oxygen gas in the air to form calcium oxide. All right. Where are we headed with this? Well, suppose we react 5.66 moles of calcium and 4 moles of oxygen gas. Determine the number of moles of oxygen left over after the reaction is complete. In order to answer this question, you need a balanced equation. And this is a word problem that gives you the names of the compounds and the elements. And if you don't know how to write them, then you can't solve the problem. So calcium metal reacts with oxygen gas. Calcium metal and oxygen gas. Notice diatomic. If you didn't know that, you may write the equation wrong. And gives you what compound? Calcium oxide. Calcium, oxygen, which is a solid. Now, is that written correctly? Yeah, calcium is an alkaline earth with a 2+ charge. All alkaline earths have 2+ charge when they're in ionic compounds. And oxygen has 2- charge when it's in an ionic compound. So just 1 and 1 is all you need. Now, what's the balance? Well, we could set up the budget, but that would be a waste of time because this is easily balanced. Element, compound. All you need is to figure out, right, we got 1 calcium. We need 2 oxygens. Now we have 2 oxygens, but we need 2 calciums now. That's balanced, quick and easy. All right, what does the problem give us? Suppose we have 5.66 moles of calcium. Okay, and we react that with 4 moles of oxygen gas. All right. The question is, how many moles of oxygen are left over after the reaction is complete? Well, that statement implies that oxygen is in excess. But maybe it is and maybe it isn't. So the way to find out which one is limiting and which one's excess is to look at the ratio, 1 to 2. So if this is 1, right? If 4 moles is 1, then 8 moles would be 2. Right? We don't have enough calcium. If we wanted to match, stoichiometrically match the 4 moles here, we need 8 moles here. But we only have 5.66. So that means that calcium is going to run out. And we're going to have some oxygen left over. Okay? So what we need to do is find out how much of that oxygen do we need to react with this many moles of calcium. And for that, you need a conversion factor. Right? Moles of calcium, moles of oxygen. What's the ratio? 1 to 2. Right? Okay. So 2 divided into 5.66. I should be able to do it in my head. But I'm not going to take a chance today. 5.66 and divided by 2. 2.83. Moles of oxygen required out of 4 moles. So we do have some left over. That's the question. How much is left over? Simple math. That's 1.17 moles of oxygen remaining. And that would be, the answer would be A in that case. All right. That was 1. Next is number 3. Sodium and water react according to this reaction. Okay, you lucked out. They actually give you the reaction. Sodium on water. Sodium is a metal, reacted with water, which is a liquid, and that produces sodium hydroxide and hydrogen gas. In aqueous solution. So when you conduct this reaction, you're going to see bubbles. Hydrogen gas is going to bubble out of that solution. And if you hold a match to it or a hot ember, it's going to burst. It's going to pop. The hydrogen is going to react with oxygen in the air and give you an explosion. What number of moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water? So we're given 4 moles of sodium, 1.2 moles of hydrogen gas. And the question is, how many moles of hydrogen will be produced? Okay. So we have to find out which one's limiting. The limiting one will give us the answer. So since we want to know a product, the best way to handle this is to say, if all of this is consumed, how much hydrogen will it produce? And then if all of this water is consumed, how much hydrogen will it produce? And the one that produces the least amount is the limiting one. And that will give us our answer from the calculations themselves. All right, we're going to go sodium to hydrogen. We need a conversion factor. And in these types of problems, the conversion factor is built from coefficients of the balanced equation. Sodium, hydrogen. Hydrogen has a coefficient of 1, correct? Yes. And 2 for sodium. So that means we would get 2 moles of hydrogen gas if all of the sodium were consumed. How about water? 1.2 moles of water. We want to convert that to hydrogen gas. And the ratio there is also 2 to 1. So that's 0.6 moles of hydrogen. This is our limiting one here. So that means we only produce 0.6 moles of hydrogen. And we have some sodium left over. That brings up an interesting question. If this sodium hydroxide is in aqueous solution, and we use up all the water, where's the solvent? You can't have a solution without a solvent. Right? So, well, this is theoretical, right? But that would be a practical problem to consider, right? You're not going to have any sodium hydroxide in solution because we're going to use it all up in that reaction. How about number 5? A. 5. In the reaction, nitrogen gas plus hydrogen gas yields ammonia. Right? This is the Haber process. How many moles of ammonia would be produced? 1.21 moles of hydrogen. 1.21 moles of hydrogen and excess nitrogen. Actually, this is an easier problem than the 2 we've already done, because you're already told this is going to run out and it's going to produce ammonia. And our conversion factor puts hydrogen in the denominator, cancel, and ammonia in the numerator, and its coefficient is 2, 3. So 2/3 of 1.21 is, let's see, 3 significant figures, 0.807. Okay, let's see. It's 5 and 6. Consider the following unbalanced equation. So we have to balance this equation first, answer the question. Let's see, we've got C2H5OH, which is ethanol, the drinking kind. And it's a gas, plus O2. Leave a little room for the coefficient. Should make carbon dioxide and water. We're making that a liquid. Okay. So for this type of problem, I think the budget would be a good idea. Let's tally it up. Hydrogen and oxygen. So we've got 2 carbons, we got 5, 6 hydrogens, and 2, 3 oxygen. On this side, we have 1 carbon, we have 2 hydrogens, and we have 2, 3 oxygens. Well, let's see if I counted those up right. That's 9, 11. 2, 7, 8, 9, 10, 11. Okay. And that's 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now, where do we start? Well, we don't start with oxygen for two reasons. Because oxygen is an element. We always hold those till the last. And oxygen's already balanced. So we either go to hydrogen or carbon. And I choose carbon. So we need 2 carbon. Balance here. Now that changes to 4, 5 oxygen. Okay. Now we balance the hydrogens. We need 6 hydrogens on that side, which means 3. 3 times 2 is 6. And then 3 more oxygens plus 4 is 7. Okay. Carbon and hydrogen are balanced. Now we need to do oxygen. How do you get 7 out of a diatomic molecule? Use a fraction. Okay. And that will give us 7. Now that we're balanced, we want to make everything whole numbers. So the way to make whole number and get rid of that fraction, this ratio is fixed. 1 to 7 halves to 2 to 3 is the proper ratio for the balanced equation. But since we want whole numbers, we want to get rid of the fraction. That means if we multiply the entire equation through by some number, then the ratio is still intact. And that number is 2, because 2 times 7 halves is equal to 7. 2, 4, and 6. Okay, so we used our 2. Now we've got 2, 7, 4, and 6 as our coefficients, and we can answer the question next. If 1.70 grams of ethanol, okay, reacts with 11.2 grams of oxygen, I'm going to put those down here. 11.2 grams of oxygen. And my abbreviation for ethanol is like that. That's the same thing. The question is, how many moles of carbon dioxide are produced? Well, since we are given exact amounts of both reactants, we have to assume that one of them might run out, could be limiting. So we have to determine that. And since the question is asking for carbon dioxide, let's convert this to moles and then to carbon dioxide, and this to moles and then to carbon dioxide, and see which one's the least. So what we need here first is molar mass. So what's the molar mass of ethanol? We have 2 carbons, right? That's grams per mole. And we have 6 hydrogens, okay? And we have 1 oxygen. So that'll give us the molar mass of ethanol. (4608) grams per mole. So that's 46.08 grams per mole. And it's inverted in this case because I need to cancel the grams. And remember, all conversion factors are equal to 1. So if we invert the conversion factor, it's still equal to 1. All right, so what do we get here? 1.7 times that. No, divided by that. There we go. So this is, make some room here. This is 3.69 times 10 to the minus 2 moles of ethanol. And I'm going to go ahead and convert it to carbon dioxide. So the ratio, the molar ratio, is 2 here, 4 there. 4 and 2. That means 2 times that value will give us 7.38 times 10 to the minus 2 moles of CO2. Okay, now we'll do oxygen. Convert oxygen. Right? 2 times 16 is 32. Right? That gets rid of that one. I'm going to go ahead and do the whole calculation together and just take the moles of oxygen, right? Moles of oxygen and CO2, and what's their ratio? Well, oxygen is 7 and carbon dioxide is 4. So if I say 11.2 times 4 divided by 32 and then divided by 7, I get 2.00 times 10 to the minus 1 moles of CO2. All right, which one's bigger? This one's bigger. This one then is the limiting one. This is the true value of carbon dioxide produced, that many moles. Now, our answers are in standard notation. So we need to move this to the left 2 places. Right? 738, is that in there? Yeah, it's E. 0.0738 moles of CO2 will be produced from this reaction, that balanced equation, that amount of ethanol, and that amount of oxygen. So we actually have excess oxygen. Okay. Number 7. I think I need a new marker. That's better. Fe2O3, which is iron 3 oxide, reacts with carbon monoxide according to this equation, and they balanced it for us. When 185.5 grams of carbon monoxide react with excess iron 3 oxide, how many moles of iron will be produced? Okay, so we need our balanced equations, definitely. Fe2O3 plus 3 carbon monoxide yields carbon dioxide plus iron. 2 of those. Let's see. 2, 3, 3, 1. Okay, that's correct. Now what are we given? Well, we're given 185.5 grams of carbon monoxide. Grams of carbon monoxide. And this is excess. We're told that in the problem. How many moles of iron will be produced? So we're looking for moles of iron. Okay. Remember, in a balanced equation, you can't move anywhere with mass. You're stuck right here until you convert it to moles. So what we need is the molar mass of carbon dioxide, which is given to us somewhere in the problem. Let's see, carbon monoxide, molar mass, 28. There we go, grams per mole. Why don't we go ahead and convert that like we did before? This is moles of carbon monoxide. We want iron. So what's the ratio? 3 of these, 2 of those. Okay. So that will give us, will that answer the question? How many moles of iron? Yep, that'll answer the question. 185.5 divided by 28 and then times 2 and then divided by 3 is 4.4. Let's see, we got 4 places. 4.417. 4.417 grams. Excuse me, moles. Yeah, moles length. All right, rounding error. 4.415 is the closest answer in that group. If I did it correctly, let's see, 185.5. Yep. Divided by 28, okay, times 2, divided by 3. Yep, I get 4.417. So the 4.415 is the closest one to it. And in multiple choice problem like this, pick the closest one, pick the best answer. Number 10. All right, refer to the following equation. All right, it appears to be balanced. You can check it to be sure. How many moles of ammonia will be required to produce 11.9 moles of water? Okay, this is fairly simple. Especially since the equation is already balanced. This produces 4 NO2 plus water. 6 water. Okay. 11.9 moles of water. And the question is, how many moles of ammonia will be required? And we have to assume, since we're not told, we have to assume that this one is excess. Right? So, as long as you've got moles in one of your reactants or products, you can go anywhere you want to in this balanced equation. All you need is coefficients. Right? Moles of water. And convert from moles of water to moles of ammonia. Coefficient for ammonia is 4, and for water is 6. So 11.9, actually that's 2/3, is 3 significant figures, 1.27 moles of ammonia. Oops. Did something wrong. How many moles of ammonia will be required? We do that again. Okay. Calculator error. Let's try it again. 11.9. That's better. 7.93. That number didn't make any sense because I was multiplying 11.9 times a fraction less than 1, and I came out with a value that was way less. It was a tenth of this. All right, so that didn't make any sense. 7.93 is D. All right. Next is 13. This one is unbalanced. We're going to have to balance this equation, I suspect. Number 13. Consider the following unbalanced equation. Okay, if 3.09 moles of silicon were produced, how many moles of sodium fluoride were also created? Okay, so we've got sodium fluorosilicate, hexafluorosilicate, right? And sodium. This is a solid, I believe. Yep, solid. Plus sodium solid. Yep, makes silicon. Plus sodium fluoride. Okay, we need to balance this equation. I think we can probably balance this equation. Well, let's do the budget. Yeah, I think that'd be safer. Sodium, silicon, fluorine. Sodium, silicon, fluorine. Yep, that's it. So two sodiums, three sodiums. The reason I decided to do the budget is because sodium is in two different places on that side. And six fluorines, so that's 7, 10. 2, 3, 9, 10. On this side, we have one sodium, one silicon, and one fluorine. All right. Let's see. If we need, let's start with fluorine. We need 6 fluorines on this side. That gives us 6 sodiums. Okay. And one silicon. So if we balance with this sodium, then we don't have to touch that one. Oh, excuse me. Yeah, that's right. That's right. So we've already got 2 sodiums here. We need 4 more. Correct? Let's see if that's balanced. It appears to be balanced. Let's see. 2 plus 4 is 6. Yep. That's 1. That's 6. This is 1 silicon, 6 sodium, and 6 fluorine. That's balanced. Okay. Now that we've got a balanced equation, we can do some stoichiometry. 3.09 moles of silicon were produced. 3.09 moles of silicon were produced. How many moles of sodium fluoride were also created? So all we need is this, silicon, and our conversion factor. Right? We want to know sodium fluoride, and silicon cancels. There's only 1 here, but there's 6 there. So 6 times that value, which is 18.54, should be rounded off 18.5. 3 significant figures. 18.5. That's moles of sodium fluoride. All right. That's number 13. Who's next? Skip a few redundant ones. Go down to 18. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum to oxide? So if we're going to decompose, remember, most often decomposition is taking a compound to its elements. So that's where we're going to go with this one. Aluminum to aluminum oxide. Now, why don't we say aluminum 3 oxide? Because aluminum only has 1 possible charge. It's a type 1, not a type 2 compound. So we don't say aluminum 3. That's redundant. We say aluminum oxide, and that's all you need. This is going to be decomposed. Let's see. It doesn't care about the state. All right, so we're going to get aluminum and oxygen. All right. So how do we get 3 and 2 reconciled? This is one of those tricks I showed you, cross multiply. Take that 2 and put it over here. Take this 3 and put it over here. That gives you 6 oxygens and 6 oxygens and 4 aluminum. So now we're balanced. All right, 31.5 grams of this compound. Oops. 41. No, 31. 31.5 grams. And we want to convert that to aluminum. We want to know the number of atoms. Number of atoms. So we have to convert it to moles first. The bridge between mass and numbers of any element or compound is the molar mass. So we have to go to moles first. So what's the molar mass of aluminum oxide? Well, let's see, 2 times aluminum, which is 2698. Doesn't give it to us, does it? No, it doesn't. And then 3 oxygens. Add those together. 26.98. And 48 for oxygen. That's 101.96 grams per mole. So down here we have 101.96. That gives us moles of aluminum oxide. But we want moles of aluminum. So we have 203 down here to cancel. And then we have aluminum here. And we need coefficients 4 and 2. That takes care of that. Now we want to convert moles of aluminum to atoms. So for every mole, there's 6.022 times 10 to the 23rd atoms. Avogadro's number. Okay, so now we can do that whole thing in one calculation. Point 6, 4 times the 2 divide, and then 6.022 times 10 to the 23rd. So I get 3.72 times 10 to the 23rd atoms of aluminum. Right, that's A. Okay. Moving on. Let's see, here we go. 23. Calculate the mass of water produced when 9.47 grams of methane reacts with an excess of oxygen in the following unbalanced equation. So we need to balance this equation. Methane plus oxygen in excess, correct? And excess oxygen, yeah. Yields carbon dioxide and water. Let's see. Yeah. CO2 plus H2O. Okay. Oh, they're making it a gas. Okay. That's okay. Now we need to balance it. Let's see if we can do this without the budget. We got 1 carbon here, 1 carbon there. That's good. We got 4 hydrogens here and only 2 there. Okay. That gives 4 hydrogens. Now we have 2 plus 2 oxygens. We need 4. There we go. That should be balanced. We're starting off with 9.47 grams of methane. And we want to find out what? The mass of water. How many grams of water? Okay. So we need to find out how many moles of methane we have first. And methane will be molar mass 12.01 and 4.04 for the hydrogens, and 16.05. Right? That changes to moles of methane. Now we want moles of water. Okay? And the ratio is 2 of these, 1 of those. Cancels that. Now we need to convert moles of water back to grams. And the molar mass of water, we've done that so many times, got it memorized. Right? That'll give us grams of water. So we can do it all in one calculation. Divided and then 2 times 18.02 times. So that's 21.3. 21.3 grams of water. That would be E. Three. Okay. Next. Skip a few. Get down to 26. All right. In the unbalanced equation, aluminum carbide plus water yields aluminum hydroxide plus methane. How many moles of water are needed to react with 206 grams of aluminum carbide? All right. So we need to balance the equation. Okay. Plus water yields aluminum hydroxide plus methane. All right. Notice we don't have any elements here. And we've got a polyatomic ion here that wasn't there on this side. So that means everything has to be broken down into elements to balance the equation. Aluminum, carbon, hydrogen, oxygen. So this one, we have 4 aluminum, we have 3 carbons, we have 2 hydrogens, and 1 oxygen. On this side, we have 1 aluminum, 1 carbon, and then 3 plus 4 is 7 hydrogens, and 3 oxygens. Okay? So where do we start? I'm thinking we ought to start with aluminum. If we put a 4 here, that makes 4 aluminums. That gives us 4 times 3 oxygens, which is 12. And that gives us 4 times 3 hydrogens, which is 12. Oops, no, it isn't. It gives us 12 hydrogens here. But it also has 4 others. Plus 4 plus 12 is 16. 16 hydrogens. Okay. How about carbon? Well, now we have 3 carbons here, and we need 3 carbons on this side. So that's 3. That's 12 hydrogens plus 4 times 3 is 12, 24 hydrogen. Okay. Now let's see, how do we get 24 hydrogens out of this one? Multiply by 12, 2 times 12. That gives you 24 hydrogen here, and that gives you 12 oxygen. 12, 24, 34. That's balanced. Okay, now we can work with it. How many moles of water are needed? So we want moles of water needed to react with 206 grams. 206 grams of aluminum carbide. So we need to find out how many moles of this there are. So aluminum, 4 times aluminum, 2698. And then 3 times carbon will give us the molar mass of that compound. Now I get 143.95 grams per mole. All right, so 206 grams of the compound, 143.95. That gives us moles of aluminum carbide. Then we can convert that moles, grams cancel. This is aluminum carbide. Then we can convert aluminum carbide to water with our coefficients. We have 12 here and 1 there. And that'll cancel this and leave us with moles of water. I get 17.2 moles of water. Okay, that would be B. All right. Next highlighted one. Doing good, I think. 29. A little detective work with 29. Consider the following reaction where X represents an unknown element. 6X solid plus 2 diborane let's see, what is that? That's a solid also. Yields whatever this is, we can't name it because we don't know what X is. And then 3XO2 plus 3XO2 gas. Let's see, what's this one? This is a solid also. Okay. What other information are we given? That's supposed to be balanced. 165 grams of X. Okay. React completely with diboron trioxide to produce 2.29 moles of this one. 2.29 moles of that compound. What is X? Well, remember, to find an element in the periodic table, you need to know one of 2 things. Either the atomic number, the number of protons. If you don't have access to that and you can't calculate it from what's given, then you go to the next possibility, which is molar mass. Molar masses are unique for most elements. And there are very few places in the periodic table where the molar masses come very close together. All right, so in order to do that, we're going to look for molar mass. So what's the molar mass of this compound? Molar mass of X. You need to know the mass and the number of moles. We know the mass right here. This is 165 grams. We need to know the number of moles. All right? So, looking here. That's the number of moles that's produced of this compound from this element. And you know the number of moles here, V4X3, and you know the conversion factor, right? 1 here, 6 there. So this will give us the number of moles of X. 2.29 times 6, which is 13.74 X. Now we can plug that in here. 13.74 moles, grams per mole. 165. And that's 12.12, rounded off 0.01 grams per mole. That is carbon. Okay? That solves 29, but I threw this other one in here as a point of interest. Let's see, let's solve that one under that same number. Because that's where you would find it. Except that one is not in your review document. I made that one up on the spot. So if we have a similar situation where we have this equation, X plus 3F2 yields what? XF6. XF6. Okay. And we know the X is 235.2 grams. 235.2 grams. And XF6 is 347.9 grams. 347.9 grams. Then what's X? Well, again, we have to go to molecular weight, obviously. So this is mass per mole. And we do have mass, 235.2 grams. We need the number of moles. Well, we can't calculate the number of moles here because we don't know what X is. We can't calculate the molar mass to make the conversion. But what we do know is Lavoisier's law of conservation of mass. Right? And what does that mean? That means that the total mass of this equals the total mass of that. So we know the mass of this, we know the total. The mass of this is just 347.9 grams minus 235.2 grams. And that'll give us the mass of fluorine. Let's see, 347.9, enter 235. 2 minus, this is 112.7 grams of fluorine, F2. So how many moles of F2 do we have? Now we can convert grams to moles. We just need the molar mass of fluorine. And that's 2 times 19, I believe. 19. So that's 38. 38 divided into that value gives us 2.966 moles of fluorine. Now we can convert that to moles of X. because we know that the ratio between the two, 1:3. This is 0.989 moles of X, and that goes right here. Right? Grams per mole. And that's 238. Three significant figures, grams per mole. So we look it up. We look it up on the periodic table, top to bottom, left to right, increasing values of molar mass for the elements. And you follow it all the way down until you find the closest one to that is uranium. Okay. Let's move along. 32. Two. Go. Which of the following reaction mixtures would produce the greatest amount of product, assuming all went to completion? Each involves the reaction symbolized by the equation. Okay, so we got the Haber equation again. N2 plus 3H2 yields 2 ammonia. Okay, which one? The greatest amount of product. So we're looking for the maximum product out of these. All right, let's say A, B, C, D, and E. What do we have? For A, we have 1 mole of nitrogen and 3 moles of hydrogen. 1 to 3. That's a stoichiometric mixture, and it will make 2 moles. Right? 1, 3, 2. 2 moles of ammonia. 5 moles of nitrogen and 3 moles of hydrogen. Okay? That amount needs 1 mole of nitrogen, but we got 5. So we got more than we need. We only need 1 of those. So 1 of these and 3 of those makes 2 of these. All right? How about C? All would produce the same amount. All right, let's see. All same. Well, we have to look at D and E first. 1 mole of nitrogen and 6 moles of hydrogen. So 1 mole here, 6 moles here, means that 1 to 3, we only need 3 of these, right? We needed 1 of these, so we have 4 left over. We need 3 of these, and we have 3 left over. So 1 and 3 is 2. And E, 3 moles of nitrogen, 3 moles of hydrogen. So 3 moles here, and 3 moles here. That's 3. We need 1 of these. We're going to have 2 left over, and that's still going to produce 2 moles. So, all the same, C is the answer. Number 33. All right. Okay, the balanced equation P4 solid plus 6 hydrogens yields pH3. 4 pH3 tells us that 5 moles of hydrogen, what? All right, so let's write the equation first. P4 solid plus 6 hydrogen gas yields pH3, correct? Gas. Well, we need 4 of these. Okay. 5 moles of hydrogen, what? Well, let's look at the answers. Cannot react with phosphorus is ludicrous. Reacts with 2.5 moles of P4. Is that right? If we convert this, let's see, this would be B. If we convert 5 moles of hydrogen to phosphorus, P4, H2, then we have 6 here and 1 there. So 6 into 5 equals 5/6 mole of P4. Reacts with 2.5 moles. No, that's less than 1. So B is wrong. How about C? Produces 3.3 moles of pH3. Oh, okay. Yeah. This is C, moles of hydrogen. Now we want to convert hydrogen to pH3. And the ratio is 4 here, 6 there. So 2/3 of that, 4 times 5 is 20 divided by 6. What's 20 divided by 6? Let's see, 3 equals 3, and 6 into 20 is 3. 3.33 moles. Yeah. All right, so that was correct. All right, and since we don't have any in there that say none of the above, well, actually cannot react, we already threw that one out because that's ludicrous. But we find that this one matches the answers, and we don't have to do D and E. Test taking technique. You find the right answer, and you know you did it properly, you did it exactly right, and you've checked yourself, then you can move on. $39. All right. Consider the reaction of magnesium metal with hydrochloric acid. Magnesium metal plus hydrochloric acid, right? Has to be an aqueous solution in order to be named an acid, to produce magnesium chloride, right? Alkaline earth, 2+ charge, halogen -1 charge, you need 2 of them. And this should be an aqueous solution also. And hydrogen gas. Okay. We need to balance it. Okay. So we're going to keep this one to the last. We're going to say we need 2 chlorines over here. So put 2 there. That makes 2 chlorines, 2 hydrogens, and that's balanced. If 4.52 moles of magnesium, right, and 4.52 moles of hydrochloric acid, reacted, how many moles of hydrogen gas are produced? Well, we can save ourselves some time because this is a very simple reaction. And what we know is for every 2 of these, it only takes 1 of those. So it would take half of this out of that. That means magnesium is excess. And hydrochloric acid is limiting, right? Because it needs to be 2 to 1. This is 2, That's more than one. That's twice one. So this is excess, this is limiting. So we can go with this one and calculate the number of moles of hydrogen gas. All we need is 2 here and 1 there, which means actually half of that value, which is 2.26 moles of hydrogen gas. And that's the question. That was the question. And the answer is C. So we saved ourselves some time by not going through and calculating how much for each one and then saying which one is the least, right? That still works, but it was excess because we knew with these equal amounts and the ratio of 2 to 1, then we could determine which one was limiting at the very beginning of the problem solution. 43. Okay. Refer to the following equation. All right, let's see. We're going to burn ammonia, right? Oxygen gas. And that's 7 yields 4 NO2 gas plus water. Yep. 6 water gas. Okay. There's our balanced equation. How many molecules of water are produced from 9.12 moles of NO2? If 9.12 moles of NO2 gas are given off, 9.12 moles. We want to know molecules of water. All right, let's put this over here. Give us more room. So we know it's this many moles are produced of NO2. How much water is also produced? Right? So we need NO2 here and water here in moles. That's 6 and 4. Right? And then it wants to know how many molecules of water. So now that we know moles of water, we can convert the molecules. Okay? You can do that all in one calculation. 9.12, 6 times 4 divided. See, that would be 13. Yep, that seems reasonable. And I get 3 significant figures, 8.24 times 10 to the 24th molecules of water. Okay, that's molecules of water. How many atoms of oxygen are represented by that many molecules of water? Exactly the same, because for every one of these, you have 1 oxygen. How about hydrogen? For every one of these, you have 2 hydrogens. So the hydrogen atoms would be twice that. $45. Let's see how much we got to go. Well, 45. Yeah. 1, 2, 3, 4, 8. Okay. I'm going to have to step it up here. 45. 10,2 fluoride is added to some dental products to help prevent cavities. Okay, so what? Manufacturers have made 10,2 fluoride first, though, before they can add it to their products. So they do it sometimes with this reaction. right? Oops, HF, sorry. HF. Hydrofluoric acid yields that, and then hydrogen gas. Is that balanced? Well, let's see. We do that, got 110, 2 hydrogen, 2, yeah, that's balanced. And now we can do some stoichiometry. How many grams of 10,2 fluoride can be made? So we're looking for mass of 10,2 fluoride can be made from 49.6 grams of hydrogen fluoride, hydrofluoric acid. Is that right? Yeah, it's aqueous, hydrofluoric acid, 49.6 grams. And 10 is excess. Okay, we need to convert this to moles before we can go anywhere. So 49.6 grams of HF, we want to convert to moles of HF. We need a molar mass, right? 19 for fluorine and 1.01 for hydrogen is 20.01. Okay, so that gives us moles of HF. Then we want to convert HF into 10,2 fluoride. And the ratio there is 1:1. Okay, so now we have moles of that. Now we want to convert back to mass, and we need the molar mass of 10,2 fluoride. So 10 is 108.71, 118.71, that's 10. And then 2 fluorines is 2 times 19. So let's see what that is. Let's see, 38 plus 118.71. Oops, too far. 118.71. 156.71. So 156.71 here. And that will give us the mass of 10,2 fluoride. So I'm going to multiply that times 49.6 and divide by 20.01. And that should be 388 grams. Okay, that's, oops. Oh, my mistake. Look here. That's 2. I was looking at the wrong one. That's 2. So it's going to be half of that. 194. 194 grams. See how easy it is to make a mistake? Pay close attention. All right, a lot of extra practice. And we're only going to look at this one. 60. Okay. Consider the following reaction. Okay, we have 2 A's plus a B, right? That yields 3 C's and a D. Okay. 3.35 moles of A and 2 moles of B react to form 4 moles of C. What's the percent yield of this reaction? All right. We're going to calculate percent yield based on moles, which I said in our lecture, I showed you that mass and moles are going to be the same calculation. Going to give you the same number if you use mass or moles. So what we need is, this is the actual amount. This will give us a theoretical amount. Okay, for every two of these, you need, for every one of these, you need two of those. So this needs to be 4. That means this is limiting. Right? There's not enough of it. So we're working from this one, 3.35 moles of A. We're going to convert it to C from A. And the coefficients are 3 and 2. So 3/2 of 3.35 is 5.03 moles. And this is theoretical. So percent yield would be equal to the actual divided by the theoretical times 100. Which is three places, 79.5%. That's the yield. Rounding error, 79.6. Pick the best answer. All right, 61. Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. So we're given 2 sulfurs, solid, plus oxygens, 3 oxygens, yields 2 sulfur trioxide. Okay. Now, 25 grams of sulfur, and we want to know the molecules of oxygen. 25 grams, and we want to know molecules. Okay, so 25 grams of sulfur converted to moles. Okay, sulfur is, and there's only one of them, so it's 32.07. That cancels grams and leaves us with moles of sulfur. Now we want oxygen. Cancel the sulfur. That's 3 here and 2 there. Okay. Now we want to convert, this is moles of oxygen. We want to convert moles of oxygen to molecules. And that's the magic number, Avogadro. There we go. So now we can do that all in one calculation. 25, 32.07 divided into it, 3 times and 2 divide, and then 6.022 exponent 23 times. So I get 3 significant figures, 7.04 times 10 to the 23rd molecules of O2. That's D. Okay. All right. Who's next? Who's next? 69. In the reaction between carbon monoxide and Fe3O4, the theoretical yield in an experiment is calculated to be 47.2 grams of iron. 47.2 grams is theoretical. Theoretical iron. Let's see. The actual yield is 37 grams. So actual divided by theoretical times 100 is what percent yield? That's the question. Calculate the percent yield. This is actually simpler than the one we did before. I get 78.4% yield. That would be D. $70. A 3.1 mole sample of potassium chlorate was, and that's a polyatomic ion, the chlorate ion. So potassium is a +1, chlorate's a -1. That's a correct formula. Decomposed according to this equation. All right. So we have 2 potassium chlorate, which is a solid, decomposed into potassium chloride and oxygen. In this case, we're not decomposing all the way down to elements. We're only going part of the way. That gives oxygen gas. And let's see, that should be a 3, yes. Okay. How many moles of O2 are formed, assuming 100% yield? So we're starting with 3.1 moles here. 3.1 moles. And the question is, how many moles of oxygen? Well, actually, this one's easier than the others we've done. What we need is a ratio. Right, this is KClO3, KClO3, and oxygen. And the ratio is 3 to 2. Right? So we just need to take 3.1 and multiply it by 1.5. 4.65. Well, round it off. 4.7 moles of O2. All right. That was simple. And let's see who's next. 71. Yeah, I think we're going to make it. When 3.4 moles of iron reacts with chlorine, according to the equation, how many moles of chlorine are required to react with all of the iron? All right, so we have 2 iron plus chlorine, 3 of those, yields 2 FeCl3. Yeah, Cl3. Okay. And we're given 3.4 moles. 3.4 moles. What we want to know is how many moles of chlorine are required to completely consume that. So we want the stoichiometric amount of chlorine that will consume this amount of iron. That's very simple. Right? Moles of iron. We want to convert it to chlorine. So iron goes down here, chlorine goes up there. We have 3 here and a 2 there. So 3.4. Well, that's 7, 5.1 moles of chlorine. All right, let's see. $71, $72 looks like it's coming up. Ammonia reacts with oxygen. Okay, we're going to burn ammonia again. All right, so let's put that up here. 72. We're going to burn ammonia and oxygen to produce NO2 and water. 6 water. And that's 4 and 7. Okay. It's a balanced equation. You react ammonia with oxygen and find that you produced 23 grams of water. Okay. And 8.52 grams of ammonia were left over. 8.52 grams remain. But this is produced. Okay. Determine the mass of oxygen reactant. Well, what we need to know is, you know what? Have you ever heard me talk about blue smoke? Word problems are designed to confuse so that we weed out people that don't understand what the problem is. They can't figure the problem because they haven't worked enough of them. They haven't studied enough. They don't know. So a word problem like this will throw you off if you let it. 8.52 grams of ammonia left over doesn't matter. If we want to know how much oxygen was required, all we need to know is moles of water and convert that to moles of oxygen. And we don't need that. Okay, we're going to convert this to moles of water. Grams, moles, this is 18.02. Okay, so this is moles of water. Now we're going to convert moles of water to moles of oxygen. So water is 6, oxygen 7. And they want to know the mass of oxygen. So now that we know the moles of oxygen, we can convert, like cancel, we can convert moles to grams. Right? 2 times 16 is 32. That's oxygen gas. Okay. Now we can do it all in one calculation. So I get 3 significant figures, 47.7 grams of oxygen. That would be B. This is what I call blue smoke. They're blowing smoke in your face to confuse you. You don't need it. All right, that was 72. Yeah, I think we're going to make it. And for this reaction, which appears to be balanced, C2H4, C2H4, and 3 oxygens. 3 oxygen. Let's see, they're putting the phases in there anyway. Yeah, phases. This is ethene. Oops, not the way you spell that. And 2 CO2s as a product, and water. 2 waters. So 1, 3, 2, and 2. And they're making this one a gas also. Okay. Now what's the problem? 5.5 moles of CO2 are produced. Okay. How many moles of oxygen were reacted? Oh, this is simple. 5.5 moles of CO2. And we want to cancel CO2 and leave us with oxygen. And the ratio is 2 CO2s and 3 oxygen. So 5.5 times 1.5. 8.3 moles of oxygen were reacted to produce that. Okay, rounding error. I get 8.3, they get 8.2. Let me make sure I calculated that right. 5.5, enter, 3 times 2 divide. Yep, mine's right. It's 8.25 rounded up to 8.3. So with a problem like this, there's always the possibility that you may say, well, if I got 8.3 and this says 8.2, that's not the same. So I'm going to pick D. If you do, in Brightspace, the system might react and count you wrong. If that's the case, and you think that you have reason, then and show me in an email your calculation, then you can get credit for that. $75. Consider the following unbalanced equation. Oh, we balanced this one before. C2H5, C2H5OH plus O2. I think this was 2 and this was 7. And CO2 and water. CO2 and water. That means we have 4 carbons. And let's see, 2 times 6 is 12 hydrogens. 6. Let's see if that works out. 6 plus 8 is 14. That's 14. 4 carbons. We have 10, let's see, 5, 6, 12 hydrogens. Yep. So that's balanced. So I didn't have to go through the budget again. 1.86 grams of ethanol. Okay. React with 14.3 grams of oxygen. How many moles of water are produced? All right, this is a case where you have to find out which one is limiting. And since we're headed for how many moles of water, the most efficient way to answer this one is to calculate how much water is produced from this, how much water is produced from that, and compare the two. So 1.86 grams of ethanol. I will have to recalculate this one. We want to find moles of ethanol. Okay. So that's 2 times 12.01 and 6 times 1.01 for the hydrogens and 1 oxygen. So 24.02 enter and 6.06 plus 16 plus 4608. 6.08. Okay. That's moles of ethanol. Now we want moles of water. And it's 6 here and 2 there. So that'll be 1.86. 6 times that and 2 divided. So I get 0.121 moles of water. Then we're going to do oxygen. 14.3 grams of oxygen converted to moles, 32 grams per mole for oxygen, because each oxygen is 16. All right, now we're going to convert that to water. And we have 7 here and 6 there. All right, so 14.3, 32 divide, 6 times and 7 divide, I get 0.383 moles of water. Okay, so this is the least one. That's the limiting one, 0.121. And the answer is E. And be sure we don't need that equation again. Save us some trouble. Let's see. That's 80. We'll come back in a second. I want to be sure. 80. Okay, that's different. 84 is different. Okay, we're going back to 80. There we go. All right, so I can erase these now. $80. Oops. That was wearing out. Might have to get a fresh one. All right. 80. Go. You react 22.5 grams of nitrogen gas, 22.5 grams of hydrogen gas, determine the mass of ammonia that can be produced from these two reactions. All right. So you have to write this equation. Nitrogen gas plus hydrogen gas makes ammonia gas. And if you don't remember from previous problems, or you don't have access to the previous problems, then you have to balance it. And this one is going to be 2 here and 3 there. All right, they're all gases. 22.5 grams and 22.5 grams. Okay, what's the mass of ammonia that's produced? All right, let's find out how many moles of each one there are. 22.5 grams of nitrogen converted to moles. So each nitrogen is 14.01. That means 28.02. I'm going to do these step by step. That's 0.803 moles of nitrogen. How about hydrogen? Well, 22.5 grams. Hydrogen is 2.02 grams per mole. Because each one is 1.01. And that's 11.1 moles of hydrogen. All right, we can tell right off which one is limiting because 1/3 of this is about 3.5, which is way more than you need for one of those. If this is 1, then 3 times that is 2.4, and that's excess. So this is excess. That means we can go ahead with this calculation and find out how many moles of ammonia. Right, so we have 2 here, 1 there, and then also we can go ahead and convert, since we know moles of this, we can convert that to mass. We just need to know the molar mass of ammonia. Well, it's 14.01 for nitrogen and 3.03 for 3 hydrogens. So that's 1704. Okay. Now finish calculating. 0.803 times 2 times 17.04 is 27.4 grams of ammonia. All right, that would be B. Right? Ooh, I got a stubborn marker that want to come loose. right. 80, 83. Fe2O3, iron 3 oxide, reacts with carbon monoxide, according to this equation. I think we did one of these earlier. When 470 grams of Fe2O3 reacts with excess CO, what number of moles of iron is produced? All right. This seems like a duplicate. All right, let's get the equation up here. Fe2O3 plus carbon monoxide yields 2 iron plus 3 CO2. I got those out of order. They put CO2 first, I put iron. But the problem still works. So we had 470 grams of Fe2O3. 470.0 grams. React with excess carbon monoxide. And they want to know how many moles of iron are produced. All right. So we got to find out how many moles here. 470 grams, and I think they gave us the molar mass. Did they not? Yes, 159.7 grams per mole. 159.7 grams per mole. That's moles of Fe2O3. Then we want to take that and convert to iron. This is the 2 coefficient, that's a 1 coefficient. And that should give us our answer. 470, 159.7, and 2 times. So that's 5.89. Of iron. Well, they used four significant figures. That's right. 5.886. Yeah. 4 significant figures. All right. 83, 84. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? All right, A says none of them are true. So how about B? 84B. And I'm going to reference the equation right there in that document. It's going to be on a split screen with this board, so I don't need to write it up there. If we have an equal number of moles of C2O6, I do need to write it up there. I think it's going to take more work. So 2 C2H6 plus 7 oxygen yields 4 carbon dioxide and 6 water. All right. So let's take a look at the answers. Equal number of moles of the 2 reactants, there's no limiting reactant. If we have equal masses, there's no limiting reactant. If we have more mass of one than the other. Okay, so 3 of the questions have to do with masses. So let's say if we have equal masses, let's do that first. Let's start from equal masses. So we have X grams here and X grams there. Same masses. How many moles does that represent? What's the ratio of moles? Well, if we say X grams of C2H6 and convert that to moles, because you can't say anything about mass unless you know the moles. All right, so C2H6 would be 2 times 12.01 and 6 times 1.01. So what's that? 24.02 and 6.06 is 30.08. 30.08. So if we have this many grams of that, then the moles equals X divided by 30.08. Okay. If we have this many grams of oxygen, X grams of oxygen, then we have 32 grams divided. So this would be equal to X divided by 32 grams. Okay. Let's just do that. This is the number of moles of C2H6, and this is the number of moles of O2. Moles of O2. Okay, so we can compare the moles now. If we have equal masses. Well, let's go back to B. If we have equal numbers of moles of these two, there's no limiting reactant. Well, if we have, let's just say we have 2 moles, equal number of moles. If we have 2 moles of this and 2 moles of that, you don't have enough oxygen. That's limiting. So B is false. How about C? If we have equal masses, there's no limiting reactant. Well, if we have equal masses, then we have X divided by 30 and X divided by 32. That's a different number of moles. Besides, you need, if this equals 1, then you need 7 divided by 2, about 3.5 times that much, right? And you don't have it. So C is also false. D, if we have more mass of oxygen than C2H6, C2H6 must be limiting reactant. If we have more mass here, no. Just because it's more mass doesn't mean it's that this is limiting, because you need 3.5 times as much mass for the ratio to be stoichiometric, right? So we can say that this one is also false. How about E? If we have more mass of C2H6, then O2 must be limiting. That's true, right? If equal masses, then oxygen is going to be limiting anyway. So if we have more mass, then oxygen will be limiting. I think that's it. Yep, that's it. All right. So next Thursday, I'll be here for the beginning of the class. See if anybody shows up and needs help.